In this video, we are going to look at another perpetuity example. So this involves one of SCU's more famous alumni, Steve Nash. So in this scenario, Steve Nash makes a $5 million lump sum donation to an SCU basketball scholarship fund. The fund pays out an income stream of $100K per year. So that means $100,000 per year, with a continuous increase of AK dollars per year. So let's see, this means $1,000. And the fact that there's a variable here probably means that maybe we're going to need to solve for that variable. Okay, so let's keep that in mind. Okay, and then it says, if SCU can secure a 6% interest rate, what value of A would make the scholarship income stream match Steve's donation? All right, so this initial donation of his, so this initial lump sum, so lump sum just means that that amount is donated all at once. So initial lump sum donation, that needs to fund this scholarship income stream forever. So we saw in the last video that that needs to be the present value of this income stream that needs to last forever. So the formula for present value was the integral from 0 to, in this case, it's infinity because it needs to last forever. And then we write r of t times e to the negative rt dt. And recall that the way we simplified this exponent was, this was coming from the fact that it's actually r times a minus t. And we know that a is 0. And a, the starting time, is 0. So I want to give you the chance to try to set up this equation on your own. So to find formulas for each of the pieces here. So pause the video for about 2 to 3 minutes to try that on your own, just to set up the equation. Find each of these formulas. 4, 3, 2, 1, pause the video. Pause it for 2 to 3 minutes and really try this. This is a step up in difficulty from the example in our last video. So it's a really good test of, can you combine stuff that we've learned previously in this new situation? And all that really makes this new is the fact that this integral is going to infinity. All right, so hopefully you did that. Hopefully you paused it for about 2 to 3 minutes. That's really important for this example. Okay, so let's talk about each of these pieces. I need to know, for example, what is r of t? I need to know what is lowercase r. And in this problem, actually, I know what PV is, what that present value, what that lump sum donation is. In fact, let's start with that. The donation we know already. It's the $5 million. But in the question, the other values of dollars are given in thousands. Like there's the 100,000 per year. There's also this $1,000 per year. So maybe let's convert 5 million to thousands. So if I need to write 5 million in terms of thousands, that's actually 5,000K. It's 5,000K dollars. So if that's unclear, one way we could see why is 5,000K means 5,000,000. So this is 5,000,000, which means I multiply 5,000 by 1,000. And that is 5 million. 6 zeros, $5 million. Okay. I think maybe another easy thing is to get R. R is the interest rate of the account, which is 6%, so that is 0.06 as a decimal. The hardest part to determine is R of t, but even that is not too bad. It tells us that there's a continuous increase of $1,000 per year. So each year, the scholarship value is going to go up by $1,000. So that means that R of t is going to be something linear. So it's going to involve the starting value of the income stream, which is 100K. So I'll just write 100, and I'll keep the units in mind. And then I need to add to that, the slope times t. So I'm writing this equation of a line, and the units are going to be $1,000 per year, so K dollars per year. But what's the slope? So the slope would sort of represent, well, what's the change in how much the income stream is paying out each year? So each year it's going up by $1,000. So that slope is A. I don't need to write 1,000 because I already have thousands in my units. Okay, and that's R of t. It's 100 plus A times t. So if it's unclear how I got this value for R of t, I'd first encourage you to pause the video for about a minute to give yourself a chance to think about it on your own. And if you still have a question about it, definitely use our resources for help. So come ask either in office hours or MLC or Piazza about it. Okay, so now that we know these values, let's plug into our equation. And that's going to give us, so the present value on the left. So I'll write 5,000 on the left. I'm already keeping in mind that the units are K dollars, thousands of dollars. And this equals the integral from 0 to infinity, R of t, so 100 plus AT, times e to the negative r, so negative 0.06 t dt. Okay, so I got this equation that I'm going to need to solve for A. So from here, I want you to pause the video one more time and see if you can work with this and solve for A. So pause it this time for 4 minutes. 4, 3, 2, 1, pause that video. Pause that video for 4 minutes to try this. This is a really good practice problem in terms of evaluating an integral, an improper integral at that because of this infinity, and then solving an equation. So it combines a lot of key concepts. All right, so hopefully you did that. Hopefully paused it for about 4 minutes to really try this question. If not, go ahead and do that now. It's super important. All right, so hopefully you did that. So to evaluate this integral, we would need to use integration by parts. Actually, I'm getting ahead of myself a little bit. Something I should do first because it's an improper integral. What I need to do is replace the thing that makes it improper with a variable. So that's the infinity. So let's evaluate first the integral from 0 to, let's replace that infinity with a lowercase k. I'm going to pick a different variable because I already have a t in the problem. That's why I'm picking something like k. So 100 plus a times t times e to the negative 0.06 t dt. And to evaluate this, let's do integration by parts. We've seen integrals like this a bunch at this point, so we're hopefully a little bit more comfortable with recognizing that, oh, this is integration by parts. All right, so we need to pick u and pick dv. So for u, I'm going to let it be this term 100 plus at, because its derivative is simpler than it. Its derivative would be, what's the derivative of 100? That's 0, because it's a constant. And the derivative of at, keeping in mind that t is the variable, and a is just a constant, would be a. And then I got to write a dt at the end. So dv is the other stuff. It's e to the negative 0.06 t dt. So v, this antiderivative, would be e to the negative 0.06 t over negative 0.06, over that coefficient of t. All right, so let's plug into our integration by parts formula. I'm going to write it here to the side, just so I can continue to see this, and then I'm going to move it up to the top of the page. Okay, so this will equal uv. So uv will give me 100 plus at, getting multiplied by e to the negative 0.06 t, divided by negative 0.06. So I'm just going to combine it all into one fraction. And this is a definite integral, so I need to indicate that I'm going to plug in the 0 and the k, and then minus the integral from 0 to k of v du. So that will give me, let's see, I'm going to write the constants in the front, which is a, and then there's over the negative 0.06. And then I still have e to the negative, scoot it over a little bit, 0.06t dt. Okay, awesome. So I'm going to carry this up to the top of the page. All right, so with this integral, I see a double negative. Let's make that a positive. And I'm going to hold off on plugging in the k and the 0 into this first fraction, just because I noticed that the second integral also has a 0.06 in the denominator, and it also has an e to the negative 0.06t. So after I do the antiderivative, I just kind of see that I'm going to be able to factor out some common terms. And that may make computing it easier. Okay, so I got the first part stays the same, 100 plus at times e to the negative 0.06t all over negative 0.06. Got to plug in 0 and the k. And then with it, and now I have a plus. The a over 0.06 is a constant, so that's just going to stay there. And now I multiply that by the antiderivative of e to the negative 0.06t, which we've already done once in the problem. It's e to the negative 0.06t over negative 0.06. And I have to plug in 0 and k. All right, so now let's factor out common terms. So we can factor out let's see, e to the negative 0.06t is common, and they also have this negative 0.06 in both of their denominators. So doing that, we get, factor it out, e to the negative 0.06t over negative 0.06, and then what's left over? From the first fraction, what's left over is just 100 plus at. From the second term that came out of the antiderivative, we're left with, let's see, we took out the negative 0.06, so now we're left with a plus. And we're left with a plus, sorry, divided by 0.06. All right, and then I got to plug in the 0 and the k. So factoring that out means, okay, now I just have to plug in to this. And this just looks a little bit simpler. Okay, so let's plug in. First, let's plug in the k. And that'll give me e to the negative 0.06k over negative 0.06 times 100 plus, remember I'm plugging in for t because t was the variable in my antiderivative. I was integrating with respect to t. So I'll get plus a times k and then plus a over 0.06. Okay, and now I've got to plug in 0 for the t. So I get minus, I'll get e to the 0 over, let's write that better, e to the 0 over negative 0.06. And then times 100 plus 0 plus a over 0.06. All right. So we can simplify this a little bit, but once we do that, we are going to be ready to take the limit. So we need to take the limit, in this case, we are going to take the limit as k goes to infinity. So let's put a limit as k goes to infinity way at the front. Ooh, it's not a great looking infinity. Let's fix that. K goes to infinity of e to the negative 0.06k over negative 0.06. And then times 100 plus ak plus a over 0.06. And then with the next term, the double negative is going to become a positive sign. And we are going to be left with 1 over 0.06 times 100 plus a over 0.06. And I have to evaluate this limit. So there's two terms here, and the thing after the plus sign doesn't have any k's in it. This is just a constant for our purposes. So this is a constant, which means that's just going to stay as it is when we evaluate the limit. So what we really need to figure out is what's happening with this first term before the plus sign. So let's do this limit. Let's do the limit as k goes to infinity of, and I'm going to, let's make that infinity better. One thing I could do to simplify this is I'm going to move this e to the negative exponent term to the bottom. So that's going to give me 100 plus ak plus a over 0.06 on the top. And on the bottom, I'll get negative 0.06 times e to the 0.06k. And now from here, I'm going to plug in. And if I plug in to the numerator, I'm going to end up with this a times k term is going to be a times infinity. And a is the amount that the scholarship fund is going up by each year. So a is a positive number. And a positive number times infinity, well, that's positive infinity. So overall, on the numerator, we have infinity plus 100 plus this other constant fraction, which makes the numerator just infinity. And on the denominator, we have negative 0.06 times e to the infinity. So negative 0.06 times e to the infinity. And e to the infinity is infinity. So numerator is infinity. Denominator is a negative number times infinity, which is negative infinity. And this is something that we can use L'Hopital's with. So use LH L'Hopital's. So that's something that we're happy with. Okay, so let's do that. Let's use L'Hopital's, and that's going to give us this equals, let me write LH over my equal sign to indicate I'm using L'Hopital's. So the limit as k goes to infinity. So I'm taking the derivative with respect to k, which means the 100 and a over 0.06, they're treated as constants. So the derivative of ak would just be a. And on the bottom, the derivative of that is the negative 0.06 stays there because it's a constant multiplying my function. And then the derivative of e to the 0.06k is going to be e to the 0.06k, but I have to do chain rule and multiply by the derivative of the exponent, which is 0.06. All right, so we are ready to plug in now. And doing that, we get a on the top. On the bottom, what do we end up with? We'll get this negative term times e to the infinity, which is going to be negative infinity. So I have some constant on the numerator, and the denominator is negative infinity, which is 0. So if you have a question about, please ask why if you do have a question. Sorry, I lost my train of thought there. I had paused the video to gather myself, but I lost my train of thought of what I was saying before. So let me just briefly explain why. So let's ignore the negative sign for the time being. By the way, this is also just a bit of a review from the previous calculus course. But think of a as being like, there's $8. And when you're dividing by infinity, you're dividing those $8 among a really large number of people. So when you do that, how much does each person get? Well, each person would get a really tiny amount. And that's why the limit is 0. Alrighty, so that said, so for this limit, now we know the limit of the first term using L'Hopital's rule is 0. And the second part was a constant, so it's still there, 1 over 0.06 times 100 plus a over 0.06. And remember that this whole thing was supposed to be equal to 5,000 at the start. So let's set 5,000 equal to 1 over 0.06 times 100 plus a over 0.06. And now we're almost there. Now it's just a bit of algebra. So I can multiply both sides by 0.06 to get 5,000 times 0.06 equals 100 plus A divided by 0.06. And 5,000 times 0.06, that simplifies nicely. That's just 300. And if I move the 100 over to the left, we get 200 equals A over 0.06. And then if I multiply by 0.06 on both sides, we get A equals 200 times 0.06. And that also simplifies to a nice value. We get A equals 12. But what were the units? The units of A were in thousands of dollars, all right, K, per year. Whoops, per year. And it's in dollars. And that's my answer. Alrighty, so in this video, we have finished our final goal, which was to do another perpetuity example, but this one being a little bit more difficult.